Greetings. This set of slides describes the MBSC digital twin model CFD created for the U.S. Navy's MIDS Link 16 data link terminal. Critical Frequency Design develops state-of-the-art communications, sensing, and processing technology equipment utilizing open systems and digital engineering. We've been selected for 7 Phase 1 SBIRs with 100% conversion to Phase 2 and awarded 1 Phase 3 SBIR. These contracts, the technologies for these contracts are free space optics, FSO, communications, advanced photonic and fiber optic components, and model-based systems engineering, or MBSE, for tactical data links and open systems. We're subject matter experts in photonics and MBSE engineering with significant experience in ACAT-1 programs. We've delivered over 100 systems to Tier 1 defense contractors. We're AS9100 certified. We have a secret facility clearance and are now in a 20,000 square foot facility in Melbourne, Florida, with labs for microelectronics and subsystem development and manufacturing. The Office of Secretary of Defense's digital engineering strategy requires MBSE systems models for military systems, yet most defense systems were fielded before this requirement and do not have this resource. Lack of a digital twin increases the time to upgrade and integrate complex systems. And the problem is especially acute in communication systems that are increasingly tasked with greater performance and bandwidth to support the C4I requirements. The original air-to-air Link 16 data link programs didn't incorporate MBSE models. By developing a systems model for the MIDS jitters configuration, the Program Management PMA 101 Program Office gained several advantages. PMA PMW 101 will improve and expand engineering support infrastructures and enable development of more efficient and agile and resilient tactical data links systems for future integration into the fleet. Model-based systems enable the levels of systems understanding that can be achieved through integrated analytics tied to model-centric technical baselines, and will support the new Department of Defense acquisition initiatives to expedite warfighting capabilities to the fleet. The Phase 1 and Phase 2 digital twin reference architecture models were created to a SDR, System Design Review, level. 3 of the use cases in the model were carried all the way through to a preliminary design level, PDR level. The use cases that were developed were for Phase 1 were coarse and fine synchronization and waveform startup and initialization. Phase 2, we added a second software CSCI and modeled the join use case as an executable simulation. The assembly level or SRU level modeling of the structure, interfaces, and behaviors allows mapping of requirements to the design. Weapon systems in the field today will continue to be enhanced and upgraded. MBSE and the digital engineering strategy are new acquisition approaches that are going to be employed in all future systems. Creating a digital twin of an existing system ensures enhancements are integrated efficiently. Digital twins are the framework that enables the OSD's digital engineering strategy. Future systems are going to be designed, developed, and integrated by a thread of digital processes that start and end with the systems model, but also include the hardware, software, and manufacturing to reduce the integration effort and increase our defense capabilities. Employing an agile systems engineering approach to the digital twin allows effective and incremental enhancements to weapon systems in the most efficient and effective way. This slide describes the SBIR's phases and options that we have performed over the last 3 years. We started out doing a skeleton reference architecture model using Magic Draw or Cameo. We then modeled the net entry and time sync use cases, of course in fine synchronization. We modeled waveform utilization and simulation, essentially startup and initialization of the waveform. We then added, for the join simulation, join use case, advanced protocols, including long-range protocols, integrating those into the terminal. And finally, we integrated the mid-terminal simulation with an external network simulation model, and we are just now finishing that. With the ever-increasing complexity of systems and capabilities, major system developments have increased in time and cost. Digital engineering has an opportunity to make drastic changes in this trend by conducting mission use cases simultaneous with system use cases, thereby validating requirements much earlier. Although model-based systems engineering is being required, the adoption can still be challenging when the value is misunderstood in an era of programmatic budget constraints. CFD is working to showcase the value of model-based systems engineering, developing a tactical data link digital twin by conducting use case demonstrations of key functionality to tie mission use cases to systems behavior, and then tying the system's behavior to the allocated requirements. These demonstrations have been made to the Navy Program Office and Tactical Data Link OEMs. With the maturity of the model, CFD is taking advantage of Navy-sponsored transition activities, such as STP, has demonstrated the model to other DoD organizations, and will work with other defense contractors to identify opportunities to utilize the current model and expand it for next-generation tactical data link architectures. One way that these digital models can be shared with partners or with the fleet is through an online library, essentially a digital store. We have created reference architecture models for the Link 16 MIDS terminal that could be extended by developers of a terminal. We've created OpenVPX connector libraries, SOSA libraries, and optical component libraries, along with maintenance procedures for optical cables, all in a digital engineering format. Unlike hardware or software products that were developed under SBIR's contracts, the digital engineering models that we have created are not directly transferable to the fleet, but the libraries that we created could be. What we provide is knowledge on how to use the digital tool for requirements development, for engineering, and for test personnel to complete their tasks. Thank you. For more information about critical frequency design's products and capabilities, please contact Jonathan Warren at the email shown below.